Have you ever just been standing outside, maybe looking up at the sky, and had that weird little thought pop into your head? Why don't I just float away? It sounds like a silly question, right? But the answer? Well, the answer takes us right to the edge of everything we think we know about the universe.
Now, the simple answer, the one we all know, is gravity. Of course, the Earth is huge, it has a ton of mass, and it's constantly pulling on you and me and everything around us, keeping us stuck to the surface. On top of that, you've got the entire atmosphere, all that air pushing down on us too. But that simple answer, it's really just hiding a much deeper and honestly a much stranger reality. So let's really get into it, because what we call gravity is actually one of the most beautiful and mind-bending ideas in all of physics, Einstein's theory of general relativity. But here's the catch. As we're about to see, it's a theory with some really big unanswered questions. We're calling it GR's unfinished business. All right, so first, let's just lock in that simple picture of why we stay on the ground, the one we're all familiar with. The basic idea we all learn in school is pretty straightforward. Earth's massive, so it creates this powerful force, this pull, that yanks other stuff with mass, like us, towards it. And then the atmosphere, which is also held in place by that same gravity, adds even more pressure, pushing down. Makes sense, right? And for hundreds of years, that was pretty much the whole story. But here's where things take a turn. See, asking what gravity does is one thing, but asking what gravity is, now that is a question that completely changes the game, and it leads us straight to Albert Einstein. And his answer was just revolutionary. It completely flips our intuition on its head. Get this, gravity isn't a force at all. And you can really see the massive leap in thinking here. On the one hand, you've got Newton's idea. Gravity is some kind of mysterious, invisible rope pulling things together. But then Einstein comes along and says, nope, there is no rope, there is no pull. Instead, he said that massive objects, like planets and stars, literally bend and warp the very fabric of reality, what he called space-time. And what we feel as gravity is just us moving along those curves. So how does this whole space-time bending thing actually work? Well, you can think of it like a constant dance between matter and space. This quote from the physicist John Wheeler just nails it perfectly. It's this incredible two-way street. The Earth isn't pulling on you with some mysterious force. What's happening is that the Earth's immense mass is creating a deep curve, a sort of valley in the fabric of space-time all around it. And you're just moving along the straightest possible path through that curved space. You're not being pulled down, you're being pushed down by the shape of space itself. And that's the core of general relativity. Space-time isn't just some boring, static backdrop for the universe. No, it's an active participant. It's a dynamic structure. The amount of matter and energy in a place literally tells the geometry of space how to behave. They're completely linked together. And wow, has this theory been successful? I mean, for over 100 years, it has passed every single test we've thrown at it. It predicted black holes decades before we ever saw one. It predicted that starlight would bend around the sun. And just a few years ago, we got the ultimate confirmation. We detected gravitational waves, actual ripples in the fabric of space-time. It really seems like the final word on gravity, except it's not. Because as powerful and as beautiful as it is, general relativity has some problems. Modern cosmologists will tell you it is absolutely not a finished theory. You could say it has some serious cracks in its foundation. And these are the big, multi-billion-dollar questions that keep physicists staring at their whiteboards all night. We know GR works perfectly for stars and planets, but does it work down at the tiniest subatomic quantum level? And maybe even more shocking, are we sure it works on the very largest scales, the scale of the entire universe? And that last question leads us to what our source paper calls maybe the most important unsolved problem in all of cosmology. It's called the fitting problem. So, what is this fitting problem? Well, here it is in a nutshell. All of our math, all of our cosmological models that use general relativity, they work best if we just assume the universe is basically smooth and uniform everywhere, kind of like a fog. But the reality is, the universe isn't smooth at all. It's incredibly lumpy. When we look out there, we see this breathtaking structure, this vast cosmic web. You've got stars and black holes clumping together to form galaxies. Then those galaxies group together into massive clusters.
And even those clusters are arranged in these gigantic filaments stretching across the universe, surrounding these enormous empty voids. Our universe has texture, it has structure.
So, to make the really complicated math possible, scientists have to do a kind of workaround. They coarse grain all that structure. Basically, they zoom out so far that all those lumps and voids just blur into a smooth average. It's kind of like looking at one of those pointillist paintings from across the room. You don't see the individual dots, you just see a single image. The problem is, what if all those lumps and bumps, all that detail you're smoothing over, are actually really, really important?
Because when you do that, when you average it all out, you get this massive mismatch, a huge discrepancy. On one hand, when we look at a galaxy, the gravity from all the stuff we can actually see isn't nearly enough to hold it together. It should just fly apart. And when we look at the universe as a whole, it's not just expanding, it's accelerating, like some mysterious anti-gravity force is hitting the gas pedal. Our smooth model just doesn't fit the lumpy reality.
And the result of trying to fix that mismatch is, well, it's staggering. To make the smooth model work, we've had to invent two completely mysterious things. We call them dark matter, which provides the extra gravity to hold galaxies together, and dark energy, which provides that strange push to accelerate the universe. And look at this chart. Together, they supposedly make up 95% of everything. All the stars, planets, you and me, all the stuff we know and can see, that's just 5%.
And it's so important to get this straight. We have never, ever directly detected a single particle of dark matter or dark energy. They are, for now, just placeholders. Some might even call them fudge factors. They are things we had to invent for our equations because our smooth, averaged-out model of the universe doesn't line up with the wonderfully lumpy and complex universe we actually live in.
And as the source paper points out, maybe the problem isn't with the universe. Maybe it's with our assumptions. The way we apply general relativity to the whole cosmos is still based on choices Einstein made 100 years ago, back when we didn't even know for sure that other galaxies existed. We're essentially using a 1917 map to navigate a 21st century universe.
But here's the really cool part. This isn't a story about failure. This is exciting. These problems, the fitting problem, the mystery of dark matter and dark energy, these are the frontiers. This is where the next huge leap, the next revolution in our understanding of everything is going to happen. Which brings us all the way back to that simple question we started with. We don't float into space because of gravity. But what is gravity, really? Is Einstein's beautiful, elegant theory of curved spacetime the final answer? Or is it just the first amazing chapter in a much bigger, much stranger, and much more incredible story that's still being written?